works. Yeah, thanks for the introduction, and thanks very much to the organizers for putting together this wonderful workshop and for inviting me to talk about my work. So we come full circle. I'll again talk about fractons as we heard about the first day, and I'll talk about Fracton Superfluids and Carrollian fluids. So there's a little bit of non-Lorentzian stuff in here as well. So this is based on work with my wonderful collaborators, and both Jelle and Stefan are here. Jay, unfortunately, couldn't make it, but much of this talk is in fact based on work that I did with Jay. So, just to recapitulate what we saw the first day, fractons are immobile. So, fracton phases of matter are characterized by certain kinds of immobility, be that total immobility or these subsystem kinds of immobility, i.e. lineans or planons. The total immobility, as we also saw on Monday, can be understood as a consequence of dipole moment conservation. Simply because, if the dipole moment is constant, well, then the position must remain constant. And an important point that I will exploit in this talk is the fact that because the space-time symmetries of such models are Aristotelian, if you want to couple them to a curved space, or you want to sort of couple them to a background so that you can vary with respect to this background to get certain responses, well, then you must necessarily consider this so-called Aristotelian geometry, and I will explain. So that's essentially a mix of, you can view it as a mix of Carroll and Newton-Catan in some sense. And we already heard a little bit about Aristotelian geometry on Monday. So the starting point is a little bit the symmetries of a fracton system, or a dipole system, if you like. So I will assume the existence of a conserved U1 current that is conserved in the usual way and satisfies a continuity equation of this form. Associated to this symmetry, there is then another charge, which is constant in time, just because this, if you plug this continuity equation into this, you take the time derivative of this thing and you plug in the continuity equation, you get that this is a total derivative that, and if you then furthermore assume that this current vanishes at the boundaries, then this is conserved. So this is 0. So that's the standard story of a conserved U1 charge. Now, if you also demand that the dipole charge is conserved, namely this thing, so the integration of the charge against the xi, then for this to be the case, just again, by taking the time derivative of this, you find that having this charge be conserved is equivalent to the existence of a symmetric object, Jij, such that the U1, the spatial part of the U1 current is the derivative of this guy. And if you just plug this into this continuity equation, you find that the conservation equation takes this form, which is in some sense the paradigmatic fracton conservation equation that we have already seen. So what if we now want these equations, so the continuity equation and this guy here, to arise as void identities for certain gauge transformations? Well, the first step is to introduce gauge fields to which these currents couple, in the sense that they arise as a variation with respect to these gauge fields. So if we have some generic fracton matter, whatever you want to call it, this phi, it's not important. If you have some action with matter coupled to these gauge fields, the variation looks like this. And then if you demand that these relations arise as void identities for a certain set of gauge symmetries, well, you must transform these gauge fields like this. So this is a standard U1 transformation, which gives rise to the U1 current conservation in the usual way. But the new ingredient is this dipole shift or dipole symmetry, which is parameterized by sigma, which transforms both the B and the Aij in this way. In some sense, this is you can view it as a Stückelberg symmetry. So you can in fact fix the spatial part of B to be 0, and then the residual gauge transformations that are left will tell you that this sigma I is in fact sort of related to derivatives of sigma. But because of the symmetry breaking patterns that we will explore later, are dependent on having these symmetries separate, we will not be doing this just yet, or in fact at all. If you then just consider the symmetries of a Fracton theory, you find that the symmetries consist of space-time translations, rotations, the U1 charge, or the generator of U1 gauge transformations, and the generator of dipole transformations. The brackets look like this, so they're all so these are all standard, right? They just tell us that the L's are rotations and that the Pi's and the Qi's transform as vectors, while the new ingredient is this bracket between the momentum and the dipole generator, which commutes into a U1 generator. This H here is central. It doesn't appear in any of these brackets. And if we sort of just ignore it, this algebra is isomorphic to the Carroll algebra, but yeah, it's an important point that the Carroll algebra and the Fracton algebra are not the same, and Carroll and Fracton theories are not the same, simply because of the role of the symmetries, that they're quite different, even though the algebra look very similar. Very good. So if the space-time symmetries, as I mentioned before, are Aristotelian, i.e. they consist only of this H, and the P and the Lij, so only rotations, spatial rotations, and space-time translations, then the curved, if you couple a theory with such space-time symmetries to a curved space, well, this curved space must necessarily be Aristotelian. And you could view Aristotelian geometry as some kind of ultimate non-relativistic space, in the sense that there is no principle of relativity. So there is no transformation that relates time and space. And you could say, okay, this maybe is a little bit of a funny name, but it goes all the way back to Penrose in the 60s, who considered a version of this. The geometric data is very similar to what we saw in the previous two talks. So it consists in this. So you have, in some sense, these time-like Vielbeine and their inverse, and then these H structures that we met before, with the difference now being that the only tangent space transformation in the system is a rotation. And they satisfy these standard relations that just express the fact that you're dealing with sort of a complete basis of your space in some sense. Associated to an Aristotelian geometry is an adapted affine connection that allows you to take covariant derivatives. It's defined in a certain way, but the details are not important. The only important thing is that we will assume, just to simplify things a little bit, that there is no torsion, because otherwise things get reasonably cumbersome to write down, and you're left with torsion terms all over the place when you write down things like void identities. So if we then want to write down these Fracton gauge fields I introduced earlier on a curved space, we just generalize them in a more or less straightforward way by saying that this previously, so Aij now becomes A mu nu, but Aij is purely spatial. So these Ij are spatial indices. And the covariant version of this is just to enforce that this projection with this inverse time-like Vielbein is zero. So this is what we mean by saying that A mu nu is spatial. Then the generalization of the transformations we saw before are also fairly straightforward. They become this. So delta B mu has a U1 part and this dipole shift, while A mu nu transforms like this, where this, what was previously sigma I becomes sigma mu, but with the constraint that the temporal projection is zero, while this H mu nu is just a spatial projector. So it projects away anything that's time-like. So that's sort of the basic ingredients of a covariant Fracton gauge field theory. Now, we are eventually interested in these Fracton superfluids. But before we go there, let me tell you a bit about how to construct fluids that couple to Aristotelian geometry, or which will lead to a notion of fluids without boosts. So if there is no boost symmetry, the velocity is it becomes essentially a new thermodynamic variable, because reference frames with different speeds are no longer related by any kind of boost symmetry. So the equation of state gets modified, and it includes now an explicit dependence on this u squared thermodynamic variable. The way I like to construct fluids is via this hydrostatic partition function approach, which involves coupling to a series of background fields, in this case an Aristotelian structure and a U1 gauge field, along with symmetry parameters consisting of a killing vector and what you might call a killing gauge, U1 gauge symmetry, such that this set of symmetry parameters preserve the background gauge field. So for example, the symmetry variation of tau would just be the lead derivative along k, along tau with respect to k, while the symmetry variation of p will involve the U1 gauge transformation as well. And by using these properties, we can construct a series of gauge invariant scalars. So we can construct a temperature that's related to the temporal part of this guy. This u squared, so the square of fluid velocity, which is related to the spatial part of the killing vector. And then finally, because we have a gauge field, we're also able to construct a chemical potential, which takes this form and explicitly involves the symmetry parameter. So this is how you construct a charged non-boost invariant fluid, or boost agnostic, because it doesn't you can sort of impose boost invariance on top of this. So in some sense, it's boost agnostic. There's no boost symmetry. Well, this is not about fractons yet. This is just about constructing a fluid on a background that's Aristotelian. So a fluid without boosts. No. Very good. The hydrostatic partition function then becomes this, where E is the measure, so it's analogous to the usual square root minus determinant of G. And by varying this object, we can extract currents. So the response to tau is the energy current, and the response to h mu nu is the momentum stress tensor. So by combining this guy and that guy, we can build the full energy momentum tensor, and the U1 current just arises as usual as the variation with respect to the so as the response to varying the gauge field. And then the Ward identities are just take the standard form. So the diffeomorphism Ward identity becomes the conservation equation for the energy momentum tensor, while the U1 Ward identity, of course, becomes current conservation. Right. Now, suppose that we want to repeat this exercise for a fracton fluid. For a fracton fluid, we have this a mu nu gauge field, and we have an additional parameter. So we must extend both the set of background fields and a set of symmetry parameters with these guys here. So there's now going to be this sigma mu k. And we again demand that the symmetry variation of the background fields is 0. So we must impose these relations here. Now, in contrast to what we had before, because of this dipole shift symmetry, we can no longer build an invariant chemical potential. And the conclusion, because what we previously had now transforms like this, and you can check that there is nothing else that you can construct. So in other words, only if this U is purely temporal is this guy invariant, in which case we don't really have a fluid velocity, so it's sort of stationary, which is in some sense what you would expect for a fracton fluid, because fractons cannot move. Or if you demand that there is movement, well, you must give up on an invariant chemical potential, in which case you're essentially dealing with an uncharged Aristotelian fluid. So there is sort of an argument, which is the thing that I'm presenting here, that the fracton fluids cannot move if it's charged. There are various other ways to see this, but this is sort of, I think, a neat way to do it from the perspective of the hydrostatic partition function. So the conclusion of this exercise is that to get something non-trivial, we in fact must break the dipole symmetry, or both the dipole symmetry and the U1. And in this latter case, you get something called an S-wave Fracton superfluid, which I will not discuss, but yeah, it's interesting as well. So if we just break the dipole symmetry, we get a dipole Goldstone. So this dipole Goldstone here I call tilde psi, and that transforms under dipole shifts in this way that you'd expect the Goldstone to transform. I'm also giving it this other symmetry, which is Stückelberg symmetry, because the Goldstone, the dipole shift is of course purely spatial, so the temporal part shouldn't matter so in order to sort of do this in a neat way, I just declare that the time component of this field is pure gauge. That's essentially what this Stuckelberg symmetry is telling us. Because if I didn't do this, I would have to take into account when doing variations that the field is constrained. So this is a nice way to get around that. With this Goldstone in hand, I can construct dipole invariant superfluid velocities, which is this guy here. So it's just like the normal superfluid velocity, except that it now involves the dipole Goldstone. And I can also construct what is a bona fide U1 gauge field, because when I add this guy here, so notice that there is no tilde, so it's the spatial projection. So this guy now eats the dipole transformation and ensures that this B hat only transforms under U1 gauge transformations. And then if you have some kind of functional to which so the hydrostatic partition function is going to be an example of such a functional, you can vary it, and then you get various responses, and this response includes notably these new ingredients, so the dipole current, so the J mu nu, and a Josephson equation, so an equation of motion for the Goldstone, which will be related essentially to the dipole ward identity. Now, explicitly, the ward identities we get are these. So this one is the one you get from this Stuckelberg symmetry I mentioned, so this funny temporal shift. While the dipole ward identity takes this form, and the U1, of course, is the usual thing. So when we impose the Josephson equation, so i.e. we sort of impose the equation of the Goldstone, this reduces to the dipole conservation, the dipole ward identity that we saw previously. Now, the currents, as I defined them on the previous slide, are not dipole invariant. So a neat trick that you can do is that you can change to these dipole invariant fields, and then you can extract currents that are manifestly dipole invariant, and that simplifies your life a little bit. And then the variation looks like this. And then when you then write down the diffeomorphism ward identity, you get something where each term is manifestly dipole invariant, which is a bit simpler to work with. And the result of this procedure is this thing here, which is just the standard conservation of the energy momentum tensor with some extra bells and whistles. Now,
sorry, can I ask a question?
Of course.
When you use these new dipole invariant combinations, the Josephson relation is now curly k equals to 0 or normal k equals to 0?
Well, it's still so the dipole equation of motion doesn't change, so that's still this non-curly k. Right? Okay. So they're completely equivalent pictures. It's just that we changed variables. So the dipole equation of motion is still going to be k equals to 0. Right, because I mean, so the big K is 0 just by virtue, because everything is now dipole invariant. So the ward identity for dipole shifts is now that this thing is 0. Right? But the dipole equation of motion is still this K.
Okay. Yeah. Thanks.
It's just a change of variables in such a way that we extract by this procedure dipole invariant currents. But it's fully equivalent, of course, to the other way of doing things.
So the word identity is still the same for the currents. The word identities are still the same for the currents.
Yeah. The word identities are the same. This is just a way of repackaging them in a way such that each term is manifestly dipole invariant.
Okay, thank you.
Yeah, thanks for the question. Now, things are a bit funny when it comes to the gradient ordering for these Fracton superfluids. So let me just highlight that this is not a surprise. This also happens for normal superfluids. But the fact that the spatial part of the gauge field is now order delta minus 1, which is a consequence of its definition. So as you recall, this guy is a combination of this guy and the Goldstone. So it's a combination of B and the Goldstone, and therefore it must have the same order as that combination. This has very peculiar consequences, as we'll see on the next slide, that will in fact imply that the fluid velocity must be order 1 in derivative. So it's sort of, so the conclusion will be that P-wave Fracton superfluids can flow, but they can only flow slowly. Another peculiar consequence of this gradient ordering is that time derivatives come with a different ordering than spatial derivatives, which was already observed by these gentlemen, of which 2 are in the audience. But the name of the game is, of course, the same as what we did for these non-boost invariant fluids. Namely, we used the background fields to construct, along with the symmetry parameters, to build invariants that then eventually go into this hydrostatic partition function construction. This proceeds as follows. So as before, we can construct a chemical potential, which is invariant under all symmetries in this way. But because of this peculiar gradient ordering of this B hat, as I mentioned, we're forced to conclude that if we want this guy to be order 1, the fluid velocity must be order derivative. So the Fracton superfluid, sorry, can flow, but only slowly. In particular, this means that when you construct the hydrostatic partition function at ideal order, you no longer get this U squared scalar that we had for the boost agnostic fluid before. So the hydrostatic partition function is then this expression, where we make the assumption that only the first term, so the linear term in this psi scalar appears. So psi is the trace of this dipole superfluid velocity, and just for simplicity, we assumed that in the hydrostatic partition function we only include linear terms in this. If you, yeah.
I come back to the flat spacetime.
Yeah.
I guess that when you break the dipole symmetry, you condense the dipole, and then when you condense the dipole, monopole can move, and you imply that monopole have to move slowly even in the flat space.
Yeah, that's the conclusion from this. Yes. At least for the P. So it's a funny thing, but so there is another class of so in the S-wave Fracton superfluid, that's not the case. That comes with a different ordering scheme, and there the fluid velocity is again order 1, I should expect. Right. So if you just do this, you get these constitutive relations, and as a matter of fact, this kind of fluid was already discovered again by these gentlemen. And they wrote down the constitutive relations and so on, and they even commented that the momentum sort of looked like a Goldstone, and indeed it turns out to be an example of a P-wave Fracton superfluid. Just to tell you that you can of course do linearized perturbations, and you find that the P-wave Fracton superfluid has these Magnon-like modes. So you have this quadratic dispersion with an attenuation term. Which is, was also nice. Great. So now for part 2, where we meet another. So there was another talk about Cheshire terms.
So before you move on to the second part, then, so I was curious about this the dipole Goldstone. So can you write like an EFT for that? And I mean,
an EFT of the dipole. You can. That's a good. It's very good. I haven't thought about what that would. So.
Because just I mean the second part of the question, because you wrote psi mu, so it's supposed to be like more than 1 degree of freedom, right?
It's a what, sorry?
I mean, it looks like a vector. So
yes.
How many degrees of freedom are there?
Yeah, so it's just so it has it has only the spatial part is physical, so it has as many degrees of freedom as you have space dimensions. The effective field theory, is a good question. So for the Carrollian superfluid not superfluid, the Carrollian fluid where boosts are broken, I can tell you that the effective field theory looks like a Horava-Lifshitz gravity, but in this case, it's going to be some kind of field theory build out of this dipole invariant A and the B hat. Maybe some kind of Predco-like model, but with these guys. No, not Predco, because now you suddenly have dipole invariant. So yeah, I don't know what you get. It's an interesting question.
Okay.
Yeah,
Okay.
thanks.
Thanks.
No, very. Any other question before we move on to the Carrollian?
So in our S-way superfluid paper, we wrote down effective action for the dipole. So.
Okay, very good. What kind of? Okay, we can talk later. But okay, very interesting. Yeah, thanks for the comment. Right. Okay. So the second part of the talk is about Carrollian fluids, yeah, Carroll refers to Lewis Carroll, and so some people think it's maybe Sean Carroll, but it's in fact Lewis Carroll. And of course, we already met the Cheshire Cat, so here he is again. So just to give you a little bit of an introduction to what Carroll symmetry and Carroll geometry is. One way to think about it is as the symmetries and the geometries you get when you take the speed of light going to 0, and in that limit, the light cone closes up, and you can sort of imagine that everything becomes ultra-local, because if c is supposed to be the speed limit of the universe, well then, if that's 0, nothing can really move. So in some sense, the naive thing that happens is that everything is stuck to a point. You can do various nice things to construct these geometries. Personal favorite of mine is this Catan geometry approach, so originally sort of started by Jelle. But you can also just take limits or expansions of Lorentzian geometry in this way that's completely identical to what Jelle showed you earlier, except that now instead of doing the expansion of 1 over c squared, you do it in c squared. So it's very similar, except dual. And for our purposes, we can view it as being obtained from our Aristotelian structure that we met before by simply imposing certain transformations that look like this, which are called Carrollian boosts. And it only affects the tau and the h with the indices upstairs. So these two guys here are actually invariant on the Carroll boosts, and together they form what's known as a Carrollian structure. So why should you care about Carrollian geometry and Carrollian symmetries? Well, okay, you decide if it's interesting, but there are various reasons why you might like it. So one reason is that, as we already heard a little bit, that if you were interested in flat space holography, Carrollian symmetries appear to be relevant. There are proposals that a dual field theory to asymptotically flat quantum gravity should have some kind of Carrollian flavor. But even just at a geometric level, if you look at the spaces that appear at infinity of flat spacetimes, they all have a Carrollian flavor. So for example, as we already, so null infinity, for example, is a Carrollian space, conformal Carrollian space, but Carrollian nonetheless. You might also like Carroll symmetries if you care about dark energy, because a hallmark of certain Carrollian systems is that the energy density plus the pressure is 0, which is the same that you have for for dark energy essentially. And another reason you might care, because I was made aware that this is something that people here like to do, is that in flat bands where the dispersion relation is such that the energy becomes independent of the momenta, the dual statement in position space is essentially that the light cones close up. So if they open in momentum space, they close up in position space, and therefore they have a Carrollian flavor to them. So there are various scenarios where Carrollian symmetries and geometry play a role. Now, just in very general terms and very general scenarios, if you have a thermal state, which essentially means that you have a thermal vector of this form, which is very much like this Killing vector we saw previously, but if there is such a thermal state with a thermal vector, well then you cannot get around the fact that boosts are spontaneously broken, as pointed out by these gentlemen, for example, and so sort of well-known folklore. But the thing that happens in relativistic fluids and in Galilean fluids is that the Goldstone associated to these boosts, the broken boosts, gets absorbed into the fluid velocity essentially via some kind of inverse Higgs constraint procedure, except for certain kinds of strange phases of matter, which are known as Frameit. So one thing about the Carrollian fluids is that here you could say that there is no fluid. So remember, everything is stuck to a point in a Carroll in a Carroll system. So you could, in some sense, view the necessity of having an independent boost Goldstone as a consequence of this, because there is no fluid velocity for the Goldstone to be absorbed into, unlike in the relativistic and in the Galilean cases. So
for the first example, can you give us the meaning of this Emil in the upper? Yeah.
This guy, the U, is the fluid velocity. So just the thermal vector is just a name we give to this combination of right. Yeah, thanks for the question. So in a Carrollian fluid, precisely because there is a priori no fluid velocity for the Goldstone to be absorbed into, it acquires a life on its own, so to speak. So it's so the conclusion is that if you want to have a Carrollian fluid, well, you need a boost. You don't, except if the boosts are broken. So you cannot get it without the broken boosts. Yeah, that's exactly. But there was some for many. It was a puzzle for some time exactly how you would get, because the thing is, and you can ask me if you're interested later, but the thing is that if you just take the C going to zero limit of a relativistic fluid, you get something non-trivial, and you get something that naively looks like it has a fluid velocity. So that was sort of a bit puzzling, and but it turns out that this fluid velocity that you would think is just a normal fluid velocity is in fact this Goldstone. So it actually has zero fluid velocity. It's just that it has a Goldstone that's potentially non-zero and behaves in some sense as a fluid velocity. So there are some similarities between this boost Goldstone and the dipole Goldstone I discussed in the context of the Fracton Superfluids. And the boost Goldstone transforms like this. So it cancels out the usual way. It cancels out it can be made to cancel out the boost transformations of this tau and this h. So let me just remark that just as we did for the dipole Goldstone, because this guy is really only spatial, because the boost is really only it's a tangent, it's a spatial tangent space symmetry. We sort of make we introduce a vector Goldstone, but we make the temporal part redundant by imposing this Stuckelberg symmetry and sort of gauging away the.
C go to zero, so the boost break spontaneously or explicitly.
Well, it's not so easy to see what exactly happens from the limit, because you don't see any breaking there really. You just get a set of equations, and then what actually is the Goldstone comes from the fluid. It's a sub in the same way that yellow was expanding the non-relativistic fields. You can do the same here. And then one of the subleading contributions to the relativistic fluid velocity actually hides the Goldstone. So in the C going to zero limit, that acquires the interpretation of a Goldstone.
So basically, mode of these extensions.
Yeah, the spectrum is a bit subtle, but yes, yeah. Anyway, with this Goldstone in hand, you can build fields that are now completely invariant under the Carroll boost and also the Stuckelberg symmetry, of course, but that's not so important. The point is just that if we make these combinations, we're suddenly back in this Aristotelian world where nothing transforms under anything, and we're effectively left with what you could call an effective Aristotelian structure, except that this Aristotelian structure now depends on the Goldstone. So there's sort of a dynamics there, and this comes a little bit back to Ricardo's questions about what is the EFT for this? And in this case, it's something that makes dynamical an Aristotelian structure, and that's essentially, as Yellow already mentioned, that's an Horava-Lifshitz theory. Right. So in the same way as we saw before, if we have some kind of functional that depends on this data, we can extract the currents and the Josephson equation here in the usual way. And very similar to what we had before, we just get, well, this now is the Carroll boost wide identity, but it looks in some sense similar to the dipole wide identity.
Emil, sorry, can I ask you something regarding the previous slide?
The what, sorry?
The previous slides, please.
Yeah, of course.
Yeah, I would like to ask you something. I don't know. I'm just trying to picture the physically.
Right.
How should I understand that? So, just then I should imagine that I just have like a Carroll system, and in some way I couple that with some thermal bath, whatever a thermal bath means, and via that coupling, I'm just explicitly breaking the symmetry, and then I wait maybe an infinite amount of time, and I remove the bath. So then that state that I have obtained is what I would call this thermal state that now is like an spontaneously broken phase.
Yeah, that would be so. It's an open question. So this is all done at the level of the symmetries, right? So exactly how to connect this to field theories and how they thermalize is an open question. It's that is remains unknown. No, thanks for it's a very important open question, I would say. Yeah, thanks. Right. In the same way as we did before, we get diffeomorphism wide entities. But notice now I don't write it in terms of a covariant derivative, and the reason I don't do this is because, well, covariant derivatives for a Carrollian geometry actually to have a proper adapted connection, you need some additional ingredients that I'm sweeping under the rug here, and you actually don't need them. So at first order, you don't need a connection, so you can get away with writing everything in terms of partial derivatives, where again, as before, this is the measure. Right, so to construct a hydrostatic partition function for a Carrollian fluid, which has this boost Goldstone, well, it's quite easy because it's exactly the same as what I showed you for these the non-boost invariant fluids, because you have this effective Aristotelian structure. The only difference is that you now have this dynamical Goldstone that you must take into account. And so you just do the standard thing. You construct the temperature and this velocity squared. And just let me again highlight the fact that unless the boosts are broken, there is no way to construct a temperature just because of the fact that tau transforms onto Carrollian boosts. So just doing this, we find that the energy momentum tensor takes this form, where I remind you that this tau hides a Goldstone. While the Josephson equation takes this form, and of course must vanish on shell. And essentially, the vanishing of the Goldstone equation of motion on is now the Carroll boost ward identity. And we see that it has two solutions. So if this is 0, either E plus P is 0 or U is 0. And it just so turns out that the limit of C going to 0 of a relativistic fluid lands you on this branch where U is 0. So E plus P is not necessarily 0. But of course, even though U is 0, the spatial part of it at least, you still have the Goldstone. And that's what people interpreted as a fluid velocity. And that's what led to some confusion. The other branch is this one where E plus P is 0 and is sort of, in some sense, more conventional. And you don't, that's what you would naively guess happens in a Carrollian system. So let me conclude. So as I mentioned, so there are lots of interesting things to do in the context of the fractons. You may recall this algebra that I showed you. So these fracton gauge fields that I showed you are actually not the ones that you get from a gauging of this algebra. You have to impose a certain additional curvature constraint to get them to match. So it would be interesting to sort of to play the same game, but to do it in terms of these more general gauge fields. And this should be related. So in this paper, they have a slightly different gauge field as well, and then this should just match what these guys do on the nose. it would be interesting to consider more general Fracton-like symmetries. So what happens if we have subsystem symmetries? Well, there you typically don't have rotations. So constructing a geometry is going to be a bit funky. How would you do that? Well, it's interesting, but there is some proposal for gauging subsystem symmetries, which could serve as a stepping stone. And of course, related to Francisco's question, how do you have a field theory understanding of this? What do Carroll QFT theory, the Carrollian QFTs thermalize? What's the deal with that? Yeah, it's a very important open question. Then, as I mentioned, there is this subtlety about needing an additional connection in to build an adapted affine connection in a Carrollian geometry. And it may be that if you include this as an extra as an extra ingredient in your hydrodynamic description, you could get something that resembles fractons a little bit more. And then finally, I think maybe this is wishful thinking, but if there is some kind of relation to flat space holography, just because this of the Carrollian relation. And let me take this opportunity to I invite you to join me into thanking the organizers of this wonderful conference.
Thank you. Can you go back? So just maybe do you have some rough ideas for this last point? How you could think about this from the bulk, this Carrollian fluid? What is your intuition, or do you have any?
Yeah, it's a great question. So it's super interesting. It's not clear if it's really if this is the right framework to use for any sort of stuff related to celestial or flat space holography. But what we did do was construct a conformal version of this Carrollian fluid. And because of this, as you know very well, this isomorphism between the BMS group and the conformal Carroll group, you can extend the transformation of the objects with a conformal rescaling and get essentially a BMS fluid. But whether that's relevant for flat space holography remains to be seen. And my personal feeling is that perhaps it's not. Thanks for the question.
Thank you.
Very interesting.
So I have a kind of like related question.
Right.
Then, so if you have like Schwarzschild, all the Hawking radiated photons were like, well, photons, whatever, radiated by the black hole at infinity, are they supposed to be like a Carroll fluid? I mean, that theory describing them like at infinity?
No. The short answer is no, I don't think so. I mean, that's going to be something slightly different. Yeah.
Can you be more?
Yeah, well, so I think you would have to consider that these are not fluids on null surfaces. I think you'd have to consider that instead.
Okay.
Thanks for that. Well, very interesting. It's under active investigation. Yeah, thanks. Thank you.